Hello everyone, welcome to our talk on forecasting firm material event sequences from SEC 8K reports. My name is Drew and this is work with my collaborator Sophie. So, as we all know, SEC required Form 8K reports firm material events, and such sequences of corporate events actually embody very rich information about corporate strategy and business processes. Yet there's severe lack of study in previous finance or computational literature that tackles the forecasting problem, which is something we take on in this research. Additionally, the textual data in 8K reports presents challenges to traditional time series models given the time series nature of our problem. So here's our problem formulation. There's a time horizon. We divide it into a memory period and a forecasting horizon. In each period, we consider a number of discrete time windows, typically months or weeks. And in the memory period, there's a sequence of events. Based on such event sequence, we would like to forecast the event sequence in the forecasting horizon. So this function is what we would like to learn in the forecasting problem. Very typical sequence-to-sequence problem. Therefore, before we address the computational model, we actually look at existing finance literature to summarize the possible event types. This is a summary of the 10 different types of major categories of material events. The last event type is really a placeholder that is needed for modeling purposes. So the model we propose is an enhanced version of the transformer model, which is a state-of-the-art sequence-to-sequence deep learning model. The adaptation we provide in this model is to accommodate the fact that in a particular time window, there are multiple events possible. Therefore, we add an extra attention layer to aggregate the input events before giving such input to the transformer model. Other than that, we use the transformer model the way it is. To compare the performance of this model and to evaluate its quality, we compare our model with two baseline models. The first model is a Markovian baseline, which is memory size 1 model, and there's a linear dynamics. And the second baseline is a relatively simple deep learning model based on gated recurrent units. And this is a classical sequence-to-sequence model. Then there's our advanced corporate event sequence transformer model, which I just showed. Okay, so to evaluate our performance, first of all, we look at the overall performance as to the uncertainty of the model in making its forecasting decisions. We use classical measures in information theory to measure the uncertainty, more specifically, categorical cross entropy and perplexity. What you can see here is that our proposed SES model actually yields the strongest performance in terms of both cross entropy and perplexity. So this is the summary of the overall performance in terms of model uncertainty. What about type-specific evaluation, in the sense that given a particular time, we would like to measure whether or not our model is capable of predicting a particular model type precisely. So we measure the standard accuracy, precision, recall, and F measure in this case. Now, one tweak in this evaluation is that because of the temporal nature of the forecasting problem, we could actually think about what we call precise evaluation and fuzzy evaluation. Precise evaluation means that we try to be very strict in the model evaluation process. The model gets only one credit only if the model predicts the right type at the right time t. With fuzzy evaluation, we give the model prediction a little bit of wiggle room. So basically we say, well, if this is the correct answer, if the model gets it right within a little bit of a fuzzy window, t minus z and t plus z, that's okay. The model gets 1 credit or 1 point. Okay, so how did our model do? This is a summary of model performance, type-specific performance when the model is instantiated with a memory period of 36 months and a forecasting horizon of 12 months. We show in this table the F1 measure here. So what you can see here is that overall, the CES model actually outperforms not only the MCMC, the linear Markovian baseline, but also the classical GRU-based deep learning model. Now, overall, after micro-averaging, the model achieves about a 58% F1 measure across all event types. Now, this is precise evaluation. Okay, this is when the model is evaluated in the most stringent fashion. It only gets 1 point if the model predicts the right event at the right period in time, in this case, in the right month. Now, what if we allow a little bit of wiggle room? In this case, let's say we say, well, the model gets 1 point if it predicts the right event type within a t plus minus 3 time window, meaning if I get the prediction within basically half year window plus or minus 3 months, the model gets 1 point. So what you can see here is that the micro average performance is much more impressive. This is something if your application scenario doesn't require very tight temporal granularity, actually this is something that can be really deployed in financial forecasting. Okay, now one of the most significant criticisms of deep learning models is that the model is a large, typically a huge black box that lacks any sort of explainability. Now, our model is a deep learning model, is a transformer model, so it doesn't really escape from that problem. However, because the transformer model internally is a attention-based model, so the attention weights do give us some explainable insights. In this case, we actually will take a company and try to open up the window of model corresponding to this company, and we look at the attention weights. Turns out that some high attention weights, as indicated by these golden arrows within the memory period actually indicate very significant events in the memory period. And these links across the memory period and the forecasting horizon actually indicate strong possible causal relationships between events. So such explainable insights can actually, we argue, become possible basis for testable hypotheses in finance studies. Okay, so in conclusion, what we presented here is a transformer-based deep learning model for event sequence forecasting. And this is a novel formulation, and we show very impressive performance on the forecasting problem. Not only did we get good forecasting performance, but also the model is to some extent capable of providing some explainable insights worthy of further economic and financial studies. There are many potential applications of the framework and the solution we developed. And certainly it goes without saying that the model and data can be enriched. For example, we can deploy much more sophisticated deep learning models, state of the art, and also the data can be enriched by incorporating other types of financial data. So if you're interested in our research, please feel to reach out to either one of us. And I hope you enjoyed the talk. I look forward to seeing you in the future in a professional conference.